Today, I am going to give you a brief introduction to artificial intelligence. My name is Yolanda Gil. I'm in the Department of Computer Science and the Information Sciences Institute at the University of Southern California. I will mark with the USC logo special things that have happened in AI here at USC. When we think about AI systems and how they work and what they're capable of doing, it's useful to consider 5 major themes that we actually use to teach AI in K-12 and organize curriculum and develop ideas in that realm. So it's very helpful to think about these 3 themes, and I'll go over them one by one. The first theme is perception. So how is the AI system perceiving the world? What kinds of sensors is it using? They may be software sensors. They may be physical sensors like cameras, microphones. So it's very important to understand how is the AI system perceiving the world and what is it able to understand or be aware of. So in the picture on the right is an image. You can see that there's markings of having detected persons, having detected a car, having detected a traffic light. However, the AI system may not necessarily know that there's a crosswalk or that this is a street scene. So what is it really seeing? Is it seeing the distance to the person? Is it noticing the perspective? So the different perception systems convert what is getting to the AI system from sensors into some kind of awareness of the situation around them. So it's very useful to start always by examining what the AI system really is getting from the world where it works. There's also a big difference between our senses as humans that we use to perceive the world and how AI systems and computers perceive the world. So we would look at this image that is in the screen and immediately tell that these people are about to cross the street. We have so much knowledge about the world, and we can anticipate so much about our surroundings. AI systems cannot always notice such things. So when we sense things about the world, the computers don't sense things in the same ways. There's many different modalities of perception. So vision is one, speech and sound is another. But there's also ways to perceive the world, for example, by reading. You can read a description of an event, or you can read some text that tells you how something works. And so text can always be another form of perception of the world. So we have to be pretty broad in terms of understanding the types of sensors and how an AI system perceives the world. Sometimes these sensors have a lot of uncertainty. So you can see the annotations in the image. The AI system is only so confident that it's really seeing a car. It may think it may be a motorcycle, it may be something else. So they're not as confident as one might think, and they may not be as confident as we might be as humans. The second theme that we reflect on when we see an AI system is how is it representing everything that it's learning about the world and everything that's coming to it from the world. So AI systems maintain some representations about the world and use those representations for reasoning. And there's many different ways to represent the world. I have an example here from a Go board. This is from a game of an AI system with the best player of Go in the world. And you can imagine representing this board as many different squares. You can imagine representing it as a matrix. You can imagine representing it as groups of different pieces or regions on the board. So there may be many different ways to represent it. There's also many different types of algorithms to look at the same kind of representation and conclude different things, maybe predict prediction algorithms, maybe algorithms that help you see what might be wrong with this image and check that it is consistent, that this is a valid board configuration. So there's many different types of reasoning and many different algorithms that one might apply. So we ask those questions of AI systems. And finally, it's very useful to think as well of how the AI system is communicating what it knows about the world and how it's modeling the world to people, because that allows for teamwork, communication, and better collaboration. So the picture at the bottom right is Anson Williams. He's the freestyle chess champion, the lead of the team. Freestyle chess was a new type of chess game where each player is any combination of humans and computers. And when Garry Kasparov was defeated by Deep Blue, he was curious about the next challenge for human players in terms of working with AI systems. And so they had these tournaments for freestyle chess. And what they discovered is that the teams that were performing best, the teams that were winning, were not necessarily the teams that had the most chess grandmasters or the most powerful computers in the team. The teams that were winning were the teams that had a better process and that understood better who could contribute better to the game at any stage. So maybe the computer was better for the opening game. Maybe one particular player was better at moving pawns. Maybe another player was better with some other kind of strategy. And so communicating what knowledge a computer has, what is it good at, how can it work with others best is a very important question, because many AI systems don't work in isolation. So this is our second theme, how is the AI system representing the world and reasoning about it? The third theme that we think about as AI researchers is how the AI system is learning. How is it improving how it works? And so sometimes they are learning before they are put out in the world to be used. Other times they are learning as they work in the world. So that's a really interesting question to ask. There's many types of learning. So AI systems can learn from data, but they can also learn from instruction, somebody telling them how something works, or from observing somebody doing a task. Or maybe they're learning from reading. They may read a lot of books and a lot of text and learn something from all that. So there's many different types of learning. Learning, it can also be done by technology and algorithms known as neural networks. And this type of learning is inspired by the human brain, and it has led to major revolutions in AI. And we'll talk about this more in a little bit. But this is our third theme. How is the system learning to improve its behavior and its performance? The fourth aspect that we consider is how is the AI system interacting with the world, and what is it conveying, what is it communicating? So really to interact with people naturally requires a lot of different kinds of knowledge, and AI systems don't always have that. So first is knowledge about how natural language works, how to understand and generate language. That's very challenging. The second aspect is nonverbal communication. So when somebody leans forward, sometimes they communicate they're really interested in what they're hearing about. There's also aspects of affect. That means the attitude towards something or the emotional state that somebody's in. So you can convey sadness or excitement and so on. And sometimes AI systems cannot convey that, sometimes they can. The third type of knowledge that's very important in communicating with people is common sense. So we call this any kind of knowledge that is very common and intuitive about the human experience and how the world works, that everybody, all people know about. So we all know that we wake up in the morning, people have breakfast, most people go to work or to school, etc. And so having this knowledge about what happens during the day and how things work is very useful. And finally, these computer systems may have a memory of prior interactions and start to develop models of people and some understanding of what people are like, their preferences, their ideas. And so it gets to an entire area of philosophy of mind and consciousness. Are these systems really having, developing some kind of mind? That's more of a philosophical question. But you can see that all of these types of knowledge about language, knowledge about nonverbal communication, common knowledge, and memory of prior interactions, all of that kind of knowledge makes our interactions more or less natural with these AI systems. So always ask these questions. An AI system that has no memory from their previous interactions is not going to have a good model of what you may prefer to do. The picture that I'm showing here is a robot called Moxie. It is made by a USC spin-off company called Embedded. And this robot was designed to help autistic children develop social skills. I have one at home. It's really fun. You can talk to it and it will be very friendly, very natural. It will communicate with you, and you can see that the robot is immediately drawn to asking you about your social interactions that day, if you saw anybody, if you met with a friend, if you made any new friends, and it will encourage you and give you hints about how to be more social. So very interesting to see how it understands that aspect of human communication. One last theme to mention is societal impact and the societal context of AI systems. So AI systems can impact society both positively and negatively, as do technologies in any area. One aspect that's very critical to consider is how an AI system is used for making decisions, especially if they concern people or there's some critical situation or costly consequences. So we have to take into account that context. So always ask of any AI system, how is it making decisions? How can people around the AI system overcome or improve on those decisions? And what is the best setting for using the AI system? The picture that you see in the middle of this slide is an example from a system called Compass that was used to predict recidivism. A company sold it to the government and it would make predictions about whether someone was likely to commit a crime in the future. And so it was used to make decisions about parole and other kinds of incarceration. And so the system actually worked in ways where it was very biased, it was racially biased, and the company that made the system insisted that they were not using any kind of features that would lead it to be racially biased. And so after many studies, it was shown that the system was behaving in a way that was racially biased. The system was a complete black box. And so being able to develop systems that have a way to look at data, but can also explain and justify the reasons for their decisions is very important, because then you can see if it's using racial features or other undesirable features to make decisions. So being able to explain how the system works and being able to understand how it made a decision. There's also a big issue on, should the AI system make a decision or be making recommendations so that human decision makers can take into account the broader context that maybe the AI system is not aware of. AI systems may have negative impact. They may be biased, but they also can have very positive impacts in society. And it's something that we have to weigh very carefully. In the middle of the slide at the bottom, there's a picture from work on looking at mammographies and how AI systems can make predictions of the likelihood of breast cancer 5 years ahead of the human diagnosis of breast cancer. So looking back at mammograms and cases in many patients, we can see that it is more likely to detect breast cancer early and minimize its effects if an AI system is used. So not using this AI system over the current state of the art is also something that we have to consider. So we should think about the benefits of AI systems and not be afraid of adopting them and incorporating them into our processes and our society. I want to also mention how AI systems can affect jobs, careers, the services that are around us. AI systems are enabling an enormous amount of services, reducing the cost of many of the services that we use, but they're also affecting people's jobs. You may have heard in the news that there's a lot of concerns about AI systems taking jobs from people. Really, AI systems are going to change the jobs that people do fundamentally. So I have a picture here of an fulfillment plant and the robots that a company, very successful AI company called Kiva Robotics, put out in the field, and really changing how humans are are moving and doing jobs in the fulfillment plant. I can think of assistants that used to be using typewriters and started to use computers to type documents, and little by little the jobs have changed tremendously and require pretty significant computing skills in terms of spreadsheets and using websites and following processes and so on. So jobs will change significantly, and it's something that we have to consider when we think of AI systems. We also notice that AI is changing our culture and is changing our world. And after so many years of doing research in AI, I see that understanding artificial intelligence gives us an understanding as well of human intelligence and what is intelligence and how people work. So I like to highlight work by USC faculty Antonio Damasio, pointing out that humans are not so much thinking machines that have some feelings, but they seem to be feeling machines that think. So our physiology and our emotional state seem to affect our decisions in a greater way than we realize. For example, there's studies of human judges that give more severe sentences right before their lunch break. And so we have to think about this comparison that we often make between an AI and a human making decisions, because it is not always clear that the rational decision made with the information available that an AI can make may necessarily be better than what a human might decide. And so we have to think very carefully about how we make these comparisons. So all of these are aspects of how AI systems are used in society, the context, and the impacts that it has on how we think about ourselves, our jobs, and our own intelligence. So these are the 5 areas that we consider as AI researchers when we look at AI systems. So I would encourage you to understand AI systems from these 5 perspectives and ask these questions. They will help a lot in understanding. So when you read a piece of news about an innovation in AI, when you learn about some AI system that is going to be used in your place of work, or when you learn about a new app or AI system that you can interact with, ask yourself these questions, learn more about this system in terms of these questions, and they will help you understand its capabilities, but also its limitations and what you should be looking out for. So the first one was how and what is it perceiving? What is the system aware of? The second one, what is it representing? What is it able to reason about? The third, what is it learning and from what kinds of data and information? What can it communicate? And what impact will it have in society? Notice that the questions are not so much about how the system works and how is it operating. Those are very technical questions that you may not be able to answer, but rather what is it doing and what is it capable of? Of course, the understanding how the system works is also very interesting, and I would encourage you to learn as much as possible about AI, since AI will be more and more present in our world moving forward. So these are the 5 areas that I would love to see you think about. I'm going to now describe AI systems that have appeared over the last 30 years that signified major milestones in AI research and AI contributions to the world. And as you see these AI systems, if you're curious, you can research about them and ask these questions and learn more about what the AI technology was at the time compared with AI technology today. So these are all things that we can all learn about in terms of AI systems. I'm going to start in the early 90s because that's the time when I was graduating from my PhD studies, and I was writing my thesis, and I was having difficulties, and I had an injury in my arms, and so I was given a speech recognition system to dictate my PhD thesis to the computer. This AI system was called Sphinx, and around 1990, it was very exciting because after many years of research in speech systems, and there were good speech systems out there, they worked only for the speaker that they were designed for. They worked in a very quiet room, and they worked with a specific microphone that was used, and one had to speak to it, breaking any sentence word by word, separating artificially the words. And I was given this experimental system that could work for me, even though it had not heard my accent and my way of speaking before. It also could talk about any topic, and I could speak continuously without having to break things word by word with whatever microphone I had at the time. So that was incredible, and a really major milestone for AI systems to be able to have that speech recognition ability. In 1992, when I first came to USC, I was very impressed. There was a team of researchers that had been developing a cognitive architecture that really looked at how humans think about tasks, how they achieve goals, how humans think about goals, decompose them, consider different alternatives to accomplish goals, and represented a lot of knowledge. At this time, this cognitive architecture for AI was being used to fly helicopters and airplanes. And at that time, it participated in an exercise where a simulation was run, and the AI systems were flying with other human-flown aircraft, and they were flying in formation. And the commanders could not tell which of the aircraft were flown by AIs and which of the aircraft were flown by humans. And so this was very interesting because there were a lot of decisions to make. If somebody was leaving the formation, you had to take their place to keep the formation intact. You had to have some ideas of how to follow whatever other airplanes you were following, how the formation was changing. So a lot of different kinds of reasoning and goals and problem solving that was demonstrated there. So that was very exciting, a very exciting AI system here at USC. Also in that year, we had an AI system that learned to play backgammon at human player levels. This was very significant because we had been trying to build AI systems that played games at the best human performance possible for a long time. This particular AI system learned to play with itself. So it had two versions of the system, and each version was one player in the game, and it played many, many games against itself, and everything that it would learn at each game, it would remember. And so the fact that the system, just through learned to play at human levels was very, very significant. And this was 1992, a very long time ago, that AI was making these big strides. In 1995, in Pasadena, in JPL, they developed an AI system that was looking at data from the second Palomar Sky Survey, and it was clustering stellar objects together based on what the system could see their features were. And so the system identified 5 new quasars that the astrophysicists had not considered before, and they made a lot of sense to them, so much so that a journal article was published with these findings from SkyCat. And so this was very exciting to see an AI system actually making a contribution to science all the way back in 1995. Also in that year was the first time that a car drove autonomously using an AI system on highways across the United States. So this car was called the NavLab. It was actually a van, and it carried a computer in the back. It had a neural network in the computer, even way back when, that had been trained to drive around roads. Mostly it learned to avoid bumping into cars that were in front of it. So it learned to detect cars in front of it. It learned to brake, because it learned by watching a human driver hit the brake when there was a car close by. And it also learned to follow the lines that separate the lanes on the road. And so this was very significant, that it had learned from watching a human drive, and then it learned autonomously. When this AI system reached San Diego, it drove from Pittsburgh to San Diego. When it reached San Diego, the students and the people that were working on it called the Tonight Show and asked Jay Leno or I guess the producers, if they wanted to have them on the show to talk about this incredible AI system that had done this. And they were told that, basically no one would be interested in this, and they were not invited to come. They ended up visiting Jay Leno and getting an autograph from him. He was very nice. But just to give you an idea of why I tell you about these discoveries, because AI has been around for many years. AI tackles very, very complex questions, very complex problems, but we've been making very steady progress over the years, and there's very solid technologies, many paths that have led to unsuccessful systems, worse performance, less interesting ideas, but many, many paths that we've explored and many accomplishments over the decades. And of course, many further open questions to pursue. Deep Blue, I want to mention this. So Deep Blue defeated the human chess world champion, Garry Kasparov, who had never been defeated before, and he got a grandmaster level rating. Chess was something that early AI researchers thought would be relatively simple to resolve. I think the first chess player program was built during the winter recess in 1959, 1960. And they thought that they could just improve it and reach grandmaster level playing. In this case, this was an AI system that also was combined with very powerful microelectronics. And so it had both the ability to see the board, think about it, consider different strategies and moves. It had a lot of knowledge about chess strategy, but also it had very fast ways to search through the space of possible moves. So it's kind of a really good example of how powerful microelectronics and powerful knowledge of chess strategy came together to achieve this major milestone. In 1999, AI flew into space. A fully autonomous AI system flew into space. It was called RAX, and it was able to plan and monitor and repair faults in carrying out various kinds of experiments. So it would route sensors and cameras in different directions to satisfy the experiments at hand. And if there was a faulty camera, then it would repair its plans and figure out how to use another camera or reorder the experiment to a time when the right camera was available. So really interesting to think about AI systems being so autonomous and commanding these experiments in space all the way back to 99. The 2000s also gave us many exciting surprises in AI. So in the year 2000, a lot of techniques about how to represent knowledge in something that we call ontologies, looking at classes of objects, properties of objects, how they are related to one another. These technologies were used to create a standard way to represent gene products and cell function and how genes affect cell function for 3 specific organisms. So they had now a standard way to talk about genes across all these organisms. And this gene ontology really led to a revolution in biomedical research, because today there's more and more types of organisms, type of genomic, proteomic, and omic information, cell function, all kinds of information that we can connect together through these shared representations. In the year 2000 as well, a robot called Kismet demonstrated and recognized the use of emotions to communicate. So you can see a picture at the bottom. It had a way to move the eyebrows. It had a way to open the eyes wider or close them more. It had a way to tilt the head to really communicate certain types of emotions, and it would recognize the emotions of its counterpart and react accordingly. So this was a very significant milestone as well. In the year 2003, there was a system developed at USC for statistical machine translation. This was an academic prototype, and yet in the machine translation competitions, it beat the best handcrafted commercial systems available. So in industry, all the machine translation systems worked with rules of translation. They targeted very specific languages. And the system really led to a revolution in machine translation. It started with languages that we have a lot of text for, a lot of data for. Parallel language, English and French, for example, from the Canadian Parliament. So languages where we have a lot of data about how the language was translated by humans. It moved to techniques to learn even from text that is not parallel. So if you had many texts that did not correspond, they were not about the same topic, but yet you had two buckets of text in both languages. It could learn from that. To today, when it can learn from languages, it can learn to translate languages where we have very little text about them, but we know that human languages have a lot of regularity in terms of how they describe and how they talk about the world and people. And so exploiting all of those commonalities to learn to translate new systems. So back in 2003, long before Google Translate, long before you had translation tools in your hands, we had them here at USC. In 2004, another branch of work that used knowledge representations created a standard for the web called the Resource Description Framework, RDF. So it used ideas from frame systems in AI, the way that we build frames about types of objects and what we can say about them, frames as a metaphor to hang knowledge about a particular type of object. So this specification became a recommendation, and it was seen as the beginning of creating on top of the World Wide Web that linked documents, a giant global graph that would link entities in ways that were machine readable. And so this continues to grow today and give us a lot of ways to support search and other tasks. I'll talk more about this in a second. In 2007, we had a winner of a race through the desert, doing off-road driving to go through in the desert from point A to point B. This race had been held for 3 years and there were no winners. So in 2007, this van that you see a picture of at the bottom of the slide won the race. It had to learn to drive when there were no lanes on the road and a lot of dust that was obfuscating its cameras. Really, really interesting piece of work, and also using powerful neural networks, but a lot of different technologies to address different aspects of driving, and very interesting system that showed significant progress in this area of self-driving cars that is of so much interest today. In 2007, there was a team of robots many teams had been participating in competitions called RoboCup. They had simulated competitions. USC won some of those competitions. They had robots of different sizes. USC also won some of the competitions for the smaller size robots. In 2007 was the first time that the robots actually played soccer in a meaningful way. And in this case, they did an exhibition game with humans. RoboCup is a competition that is aiming to play soccer with a human team in 2050 and win. And so this was an exhibition game where you could see the robots actually moving and trying out some plays. They were not capable enough to win a game or to do something significant in soccer, but it was a milestone in this competition because in the past the robots would just be in the field and not move very much or not do very much significant. So this was very nice to see. This requires the robots to see the world, understand how to coordinate and move, how to pass the ball. Really, really challenging. In 2009, there was another competition put out by Netflix to give $1 million to whoever built a system that predicted the kinds of movies that people would watch based on the movies that they had watched before and that they had liked before. So Netflix put out the data set and made it available and kept, without revealing, data set for some of their customers, and they use that for testing. So people would send them a system and they would run it and they would say, yeah, I didn't do very well. It only succeeded at 50% of the cases. And so a lot of the teams were wondering how to improve their own approach and their own technology. Each used different machine learning algorithms. And what happened is that two of the teams got together and discussed, they shared some information. They were competitors, but they decided to cooperate and shared how they did this. And in the process, they created a joint approach that combined both of their approaches in what is called an ensemble learning algorithm. This is a very powerful idea that is used today a lot, which means that there may not be one single way to learn, but there may be many ways and they complement each other significantly. And so maybe you look at the output of both algorithms and then you see which one is more confident, or if you have several algorithms, you may take a majority vote and that's your prediction. Lots of very interesting ideas in terms of learning from ensembles even today. But this was a very significant milestone. In the 2010s, there were also a lot of interesting progress. Siri was released in the Apple store in 2010. I had been working with the group that created Siri. The first version of Siri was really intended to do tasks for you, to make reservations at restaurants, to schedule meetings, to actually accomplish things for you. Today, it's more of an app that helps you with answering questions rather than doing tasks for you. But at the time, it was very exciting because it understood goals and tasks and accomplishing them, and did all this with a voice-activated interface. When I saw this in the Apple store at the time, I was very excited because I realized that AI had moved from being this research area, this area of research in computer science, where we mostly worked in the lab, and there were very specific applications in companies from AI, some of them that cost a lot of money to deploy. to seeing AI accessible to anyone in the world for just very little money, and it would actually work for you, and you would have it at your fingertips. And this was very, very significant and very exciting, I must say, to see Siri then be acquired by Apple. Steve Jobs had a big hand on that. He really believed that voice activated systems were the future and really wanted to invest in this. To seeing it today used and all the voice activated systems that we have today is very exciting. Lots of work to do to make them understand us better and to really understand what we need and what we mean. But nevertheless, back in 2010, this was a huge milestone. In 2011, if we go back to soccer playing robots, there was a team, CM Dragons, that actually had a team of 10 robots that really worked together, passing the ball, doing interceptions, scoring. They really got down. The collaboration, the teamwork was really, really impressive. And in previous editions of this robot soccer RoboCup competition, as I mentioned earlier, it was really hard to see that the robots were really coordinating and really playing soccer at decent levels. So this year was really, really significant and very exciting to see. A completely different type of intelligence, right? Which is this collaboration and this coordination that it takes to, in real time, do a task together that requires so much coordination. In 2011, a system called Watson took first place in a Jeopardy game, defeating the 2 human Jeopardy champions that came to play with it. So this was done during the Jeopardy program. And as you know, one chooses a category, is shown an answer, and one has to generate a question that results in that answer that you are shown. And this really required a system that knew about history, historical events, sports, literature, lots of different topics. And it had learned all of this by reading. So the system was trained on lots and lots of text, and it was trained to form questions from answers. It was designed in a very clever way, but it was very significant because it was a system that had an incredible amount of knowledge that it had learned and could play at the level of the best champions at this game. Really, really exciting. In 2012, something very significant happened, and I'll get back to this because it was the beginning of this neural network revolution, this deep learning revolution that we have today. So in 2012, there was a competition, a challenge for recognizing objects in images, and there was a system called AlexNet that did 10 points better than the next system that was out there. One of the reasons was that it used an incredible amount of data. So it used a lot more images to train than ever before. And of course, these images that it learned from had to be annotated to say, in this picture, this is a person. In this image, this is a car. In this image, this is a tree. And so it had to have significant amounts of annotated images to learn, but it did an amazing feat of going 10% points above. So that was very significant. And again, I'll talk more about this in a second. In 2013, there was a study of a cognitive tutor system. This AI system showed that it was tutoring algebra for about 20,000 students in many schools, and it raised the average scores of the students by 8 percentile points. This was incredible. Think that this AI system not only had to understand algebra and how to solve algebra problems and how to understand the different steps that you have to use to come up with a solution to an algebra problem, but it also had to have knowledge about the kinds of errors that the students would make and how to explain why that was an error and how to correct those errors and how to check that those errors had been corrected in the students' minds. So really, really exciting and very significant. There's lots of AI systems used for education out there, but this was already back in 2013. In 2016, very significant, we learned that Google had a big knowledge graph. So these are ideas from, I mentioned earlier, this graph of entities of interest on the web, in addition to the web itself, which is a graph of documents, a network of documents. Here, it's a graph of entities. So a knowledge graph would represent nodes that are people or locations or books that people have written or many other things. And so it was revealed that Google was using their knowledge graph as a way to resolve 1/3 of its searches. So 100 billion monthly searches, 1/3 of that, that's a lot of billions of searches that these graphs that have explicit knowledge and a representation of here's Abraham Lincoln, here's a location where they were born, here's the year where they were born, here's a book that they wrote, etc. So having that knowledge really helps in helping people find and locate information. In many ways, it helps disambiguate what one is looking for and also find related information. In 2019, one of my postdocs went off to found something called Wikidata at the Wikimedia Foundation a few years earlier. And in 2019, Wikidata was collecting very concise statements called triples. So, for example, USC is located in Los Angeles. That is a triple. It has three pieces of information: USC, Los Angeles, and that they are related by being located there. So it reached 8 billion triples and 880 billion edits. And it's a sister project of Wikipedia in the Wikimedia Foundation. And what's very significant is that it started being a side project where people would input information, but there were very few editors, and little by little, people realized that it was very powerful to be able to structure the information in Wikipedia beyond the text that you saw in the pages. So if you look at Wikipedia on the right-hand side, there's what's called an info box that starts to look a lot like very structured information that you see in Wikidata. And when you do a search in Google, you start to see also these graphs of information that relate entities. So all of these are ideas that came from AI knowledge representation. That is very exciting. Wikidata, by the way, just turned 20 years old in October of 2022. And it's a huge celebration to see that success. I remember when it was started here at USC, Danny Brandachik, who conceived this idea, wanted to call it Shortipedia because he thought that these triples were very short and to the point rather than long sentences that we would find in Wikipedia. And we did get an award for this system and how creative it was. So let's talk for a little bit about the current trends in AI and why everybody's paying so much attention to AI. I've given you 3 decades of incredible accomplishments in space flight, in education, in playing games, in the web, in all kinds of areas. And so, what has changed and what is exciting these days. So I want to describe to you how AI systems learn through neural networks and how that has led to a revolution. So I'll spend a little bit of time on that. In around 2012, I was talking earlier about AlexNet and the revolution that it caused. So imagine that you have a system that has units. These are these nodes in this graph, and the units represent the input. The input may be an image, and you're trying to teach this unit what is a pet and what isn't a pet. So you show this image, and every unit in this network is going to look at its inputs and then output a signal that affects the next unit in the next layer. So there's vertical units that form a layer. So the units can have many interconnections, and so they pass on all the information all the way to the end. And as you can see, you can say, yeah, this cat can be a pet. A raccoon, no, that's not considered a pet. So you train it on positive and negative examples. And when it knows this, it goes back and it adjusts all of its weights to be able to tell on its own what is a pet and what is not a pet. So there's lots of algorithms that tell it how to adjust those weights and different ways to design how many layers, how many units, how many links among them, and so on and so forth. So very roughly, that's how these neural networks are created and how they are trained. So now when you have a new picture, you can show it to it, and then it will work. The signal of the picture in the input units will be triggering signals throughout the network. And at the end, it will say yes or no, this is a pet. Sometimes people want to look at these networks and see if you can actually poke and see that this is the unit that recognizes what an eye is. This is a unit that recognizes what the feet are. These neural networks are getting more and more and more complex over time. It gets more and more difficult to even see this kind of thing. And, in the human brain, there's no single neuron that is recognizing what an eye is. There's many neurons. There's a lot of redundancy. So sometimes it's really hard to know and to understand why this neural network produced the right answer and another neural network did not. It's really hard to understand how they work. But it's a very experimental area. You try different things, you look at different things, and there's more and more methodology being developed for how to develop these networks. And certainly for engineering and science research, there's a lot of very exciting research on how to incorporate physics laws and theories about the world into these networks so that they are consistent and they can build on this knowledge that we all have to learn more efficiently, or when there's not enough data. I want to show you that on the bottom right, this is a system that we started to see in 2015, was the first publication. You have a link at the bottom that you can use to find out more about it, but it was learning from images about the artistic style of certain painters. And so you have this picture, Starry Night of Van Gogh. The system would be shown many pictures of Van Gogh, and it would take a picture of any other scene and kind of transform it until it became what you see in the center bottom of the slide, really very much in the Van Gogh style. So really impressive that it captured something that was beyond whether these were houses or some other kind of scene. And I want to spend a little bit of time talking about the more recent milestones that we have seen that will give you an idea of how AI is accomplishing things that are really exciting. So in the year 2020, a model built with a neural network called GPT-3 generated text that was very hard to distinguish from human text. GPT-3 was trained on data from all over the web. It was really enormous. You can see 175 billion parameters, really different ways to transmit these signals across the units in the neural network, so to speak. And you ask it questions. So I have here examples in blue of things that GPT-3 knows about USC. So we said, write 2 paragraphs, describe USC's world-class computing facilities, and it wrote what you see. I compressed it, but it was 2 paragraphs. And then describe USC's high-performance computing center, and then describe sustainability research at USC. So really impressive that it knows so much. It knows that there's an Office of Sustainability. It knows about all these projects, the computing center. So really impressive that a model like this can be asked any question and have all this knowledge. Really, you can ask it to add 2 numbers and it will do so. It has an incredible amount of knowledge. In 2021, a language model called BERT was used in almost every search query in English by Google. So very, very significant that these language models really helped in helping people find information. These models are very, very large. They're not necessarily available to us to do research on. And almost any big tech company has developed one of these models by now. This year, 2022, there's one of these AI models called DALL-E that you can give it a natural language description of something and it will generate an image for it. So you describe a scene in words and it generates an image. Really, really interesting. The images sometimes are not, we know that they're not realistic or real. It's very obvious, but nevertheless, really interesting how it's understanding how to put together an image that could be plausible. So we'll see what next year brings us and all the exciting things that are to come. In USC, many years ago, 2009, we actually had a paper on a model for statistical machine translation that had 11,000 features or parameters. So at the time, 11,000 seemed like an incredible amount. Compare that to today's models, they have billions and billions. They get larger and larger over time. And USC won a Best Paper Award for this. It's very exciting to look back and see that. And what happens is that these models, the larger they get, the more kinds of tasks they're able to do. And so, at some point they become so large that they know so much about language that you can ask them to make a joke about something and they will. So really exciting to see all the research questions that these models are prompting for us. So this was a very quick description of AI over time in the last many years, I think one of the things that I would like you to take away is the diversity and breadth of AI research over time. We have many technologies in AI that have done incredible things, a lot of exciting new ideas that are coming out, but certainly we have done incredible work in vision, sensing, reasoning, language, speech, representation, dialogue, prediction, learning, cognition. It's really exciting to see all this range of technologies. And again, as I mentioned, always think about these 5 dimensions, 5 areas or themes when you look at any AI system, and it will help you learn more about it. If you are curious to learn more about AI, I recommend these books. The one on the left describes to you how AI researchers created AI systems that beat the best humans at 7 different games. Very exciting to see the human side of the story in addition to the AI side. The book in the middle talks about causality and how we can use AI to understand cause and effect. Very important topic for engineering and very exciting for AI. The book on the right is a history of AI written by an AI researcher, so it's very accurate and very technically very precise and entertaining and fun to learn about. Additional materials, there's some free materials in YouTube. There's a documentary on AlphaGo. It walks through how the best human player was defeated by an AI system, but the documentary walks you through how the team of AI researchers worked together, how the human was approaching this game, and it has the human side on both sides of the game. It's very, very well done, very interesting. There's a podcast, Judea Pearl, explaining ideas on cause and effect, and really well done, and you'll find it very accessible, and it will help you understand why it's so hard for AI systems to take into account all the knowledge that one needs to understand complex systems and complex ideas. And on the bottom, if you're curious about these new AI models and AI systems that understand language, you can watch this brief video from the New York Times on prompting these AI systems to generate Thanksgiving recipes. They actually created the recipes and tested them, and so you can have an idea of how they work. In my opinion, anything that goes wrong in that experiment is actually the fault of the human. In this case, the human that asked specific questions to the AI system. So you be the judge, and it's interesting to think about how the interaction occurred and how the system works, etc. If you're interested in more topics regarding ethical concerns about AI, there's a great talk on fair questions that you'll learn a lot about. And then finally, on the topic of health, just using a very tangible and concrete topic, you can learn about how AI is changing healthcare from various perspectives, from policy, from the relationship between the doctor and the patient, to diagnosis, to hospital systems, processes, and so on. And so it will give you a pretty comprehensive view of how AI can be used in a particular domain, such as health, across the board. And then finally, if you're curious to learn more about AI at USC, you can find in those links many short videos that give a quick overview of AI faculty at USC in related topics. And I hope you enjoy them. Thank you for joining me today, and see you next time.